Matter can exist in various states. Atoms at high temperature always form gases. If you cool the gas, it becomes a liquid. If you cool the liquid, it becomes a solid. But under certain circumstances, if you cool atoms far enough to extremely low temperatures, they undergo a very strange transformation. They undergo an identity crisis. So let me show you what I mean by an identity crisis. When you go to low temperatures, the quantum mechanical properties of the atoms become important. These are very strange, very unfamiliar to us, but in fact, each one of these atoms starts to display wave-like properties. So instead of points like that, you have little wave packets like that moving around. It's really difficult for me to explain just why that is, but that's the way it is. Now, as you go to very low temperatures, the size of these packets gets longer and longer and longer. And then suddenly, if you get them cold enough, they start overlapping. And when they overlap, the system behaves not like individual particles, but particles which have lost their identity. They all think they're everywhere. This little wave packet over here can't tell whether it's this one or that one or that one or that one or that one or that. It's there and it's there and it's there. They're all in one great big quantum state. They're all overlapping. They're all doing the same thing. And what they're doing, to a good approximation, is they're simply sitting at rest. This Bose-Einstein condensate is very difficult to imagine or to visualize. I can imagine what it's like to be an atom running around gaily, freely, bouncing into things, sometimes going fast, sometimes going slow. But on the Bose condensate, I'm everywhere at once. I've lost my identity. I don't know who I am anymore. I'm at rest, and all the other atoms around at rest, but they're not other atoms around. We're all just one great big quantum system. There's nothing else like that in physics, and certainly not in human experience. So just to think about this causes me wonder and confusion.
Dan Kleppner and his MIT colleague Tom Graytak began to try to make a Bose-Einstein condensate in hydrogen.
As we started out the search for Bose-Einstein condensation, our enthusiasm grew because hydrogen seemed like such a wonderful atom to use. It had everything going for it. It had its light mass. That means that the atoms will condense at a higher temperature than other atoms would. The atoms interact with each other very, very weakly. All the signals seem to be pointing to the fact that hydrogen was the atom for getting to Bose-Einstein condensation.
Kleppner's idea was to cool the hydrogen atoms by making use of their magnetic poles. He used a strong magnetic field to create a cluster of atoms in a cold trap. Unfortunately, sometimes one atom flipped another, which triggered a release of energy that raised the temperature.
It was a frustrating time for us because our methods were so complicated. We were having a hard time moving forward.
Now others decided to take up the challenge. Two physicists from MIT met in Boulder, Colorado, and came up with a different approach to the problem. Rather than focusing on the lighter atoms of the periodic table, they hit upon the idea of using much heavier metallic atoms, like rubidium and cesium. But would using these giants enable them to reach closer to absolute zero?
The idea in the field in those days was that the light things like hydrogen and lithium would be easier. And there were some good reasons for thinking that, but we had other ideas.
Yeah, sort of gut intuition in some sense.
Their plan was to use a laser beam to cool the atoms, a technique that had already been tried by physicists at MIT. Lasers are usually associated with making things hot, but if they are tuned to the same frequency as atoms traveling at a particular speed, lasers can cool them down. When the stream of light particles from the laser hits the selected atoms in the gas cloud, they slow down and become cold. Laser cooling was a new tool that had the potential to reduce the temperature of a gas to within a few millionths of a degree of absolute zero. But Cornell and Wyman were not the only ones excited by this prospect. A new scientist had arrived at MIT.
It was in late 91 or early 92 that we had an idea how a different arrangement of laser beams would be able to cool atoms to higher density. And it worked. And this was really a trigger point. I will never forget the excitement in those group meetings when we discussed what do we next. Because with higher density, there are many things you can do. Could we now push to Bose-Einstein condensation? You see, well, lots of cables and electronics.
All the resources of Ketterle's lab were redirected to make a condensate in sodium atoms.
And right here, this is an atomic beam oven. What is wrapped in tin foil is a little vacuum chamber where we heat up metallic sodium so the metallic sodium melts and evaporates. And it's ultimately the sodium vapor, the sodium atoms, which we tried to Bose-Einstein condense.
MIT, Boulder, and several other labs were chasing the same goal. It had echoes of the race to produce liquid helium almost a century earlier.
As I tell my students today, anything worth doing is worth doing quickly because science moves on and we're all mortal and you want to do things.
While MIT was installing its sophisticated lasers, Carl Wyman's approach was small is beautiful.
In some cases, he was ripping open old fax machines and taking out the little chip inside that made the laser and showed that you could take these lasers and put them into a home-built piece of apparatus, stabilize the laser, and use them to do spectroscopy and laser cooling.
This is actually our first, what's called the vapor cell optical trap. You can see it's kind of this old cruddy thing, pulled together glass, where we could send laser beams in from all the different directions and have just a little bit of the atoms we wanted to cool.
As well as bombarding the atoms with lasers, they also trapped them in a strong magnetic field.
We would try this sort of magnetic trap, that sort of magnetic trap, this sort of imaging, that sort of imaging, that sort of cooling. All those things we could do without building a whole new chamber each time. We tried literally 4 different magnetic traps in 4 years, instead of having a 3 or 4 year construction project for each one.
By being fast and flexible, the Boulder group hoped to beat their old lab at MIT. But MIT had its own plans.